What if the closest star to our sun wasn't just a point of light, but a question Richard Feynman could never answer? You know Feynman, the irreverent physicist who played bongos and deciphered hieroglyphs in his spare time. The genius who explained quantum mechanics in ways anyone could understand. Feynman had answers for almost everything, but something troubled him, something he rarely mentioned. Alpha Centauri. Seems simple, doesn't it? Our stellar neighbor, 4 light-years away, the cosmic next door, 3 stars dancing together in the void. Nothing special. But Feynman knew something most people ignore. Imagine you're standing outside on a moonless night in the southern hemisphere. The sky is an ocean of luminous points. And there, near the Southern Cross, something particularly bright shines. It's not 1 star, it's 3. Alpha Centauri A, yellow, almost a twin of the Sun. Alpha Centauri B, smaller, orange, orbiting its companion in an 80-year dance. And Proxima Centauri, a red dwarf so faint you'd never see it with naked eyes. 4 light-years. Sounds short. Feynman chewed on numbers, and the numbers are disturbing. Light travels at 300,000 kilometers per second. In an entire year at that speed, it covers 10 trillion kilometers. Alpha Centauri sits more than 4 times that distance away. 40 trillion kilometers of absolutely nothing. If you drove there at 100 kilometers per hour, it would take 48 million years. Voyager 1 would need 70,000 years. By the time it arrived, human civilization probably wouldn't exist anymore. And Alpha Centauri is the closest star system there is. Physics said one thing, human intuition said another. And when they collide, something interesting is usually hidden in the crack. Alpha Centauri A is nearly identical to our Sun, same temperature, same color. The kind of star that should harbor planets where life could flourish. But Alpha Centauri isn't a simple system. It's triple. 3 stars disturbing the space around each other, creating an environment where, according to the models of Feynman's era, planets shouldn't form at all. The question Feynman asked was more fundamental than whether planets existed there. It was about what Alpha Centauri's very existence revealed about the rules of the universe, about what proximity means in such a vast cosmos. If the galaxy were reduced to the size of the United States and our sun were a grain of sand in New York, Alpha Centauri would be another grain centimeters away. Should be easy to reach. It isn't. That discrepancy kept Feynman awake. He never wrote a formal paper about it. But in private conversations, in blackboard scribbles, the same question resurfaced. What are we missing? Feynman died in 1988 without seeing the revolution to come. Without knowing the instruments he helped make possible would one day look directly at Alpha Centauri. In August 2024, the James Webb Space Telescope turned its golden mirrors toward our stellar neighbors. What it found left scientists unsettled. But before I tell you what was discovered, you need to understand why this discovery was considered nearly impossible. Why the very attempt was seen as irrational optimism. Because Alpha Centauri's story isn't just about stars and planets. It's about the limits of what we can know. About what happens when you point your best instruments at the nearest abyss and discover the abyss is staring back. To understand what the James Webb found, you need to understand why finding anything was considered almost a miracle. Imagine you're trying to photograph a firefly hovering 3 centimeters from a stadium floodlight. A 500,000-watt light aimed directly at your eyes, and you're standing kilometers away. That's the problem with direct imaging of exoplanets. A star like Alpha Centauri A shines trillions of times brighter than any planet orbiting it. Trillions. The disproportion doesn't fit human experience. That's why most exoplanets were found through indirect methods. The transit method detects the planet's shadow passing in front of the star. The radial velocity method detects the gravitational wobble the planet causes. They work, but they don't show the planet directly. They don't let you study its atmosphere or composition. For that, You need direct imaging, and direct imaging is absurdly difficult. Feynman understood this. He spent his career working at the limits of measurement, on how to extract tiny signals from overwhelming noise. He knew that seeing a planet around another star wasn't just an engineering challenge. It was a challenge to the very limits of what light allows. And Alpha Centauri complicated everything. Being a triple system, when you block the light from A, you still have to deal with scattered light from B shining nearby. 2 floodlights instead of 1. Gravitational models added pessimism. The dance between A and B would create instability zones, preventing planets in interesting orbits. The habitable zone seemed particularly unlikely, so why try? Because Feynman taught something else. Theories are just theories until you test them. The James Webb was the first instrument capable of this test. Its gold mirror reflects infrared light, where a planet is thousands of times fainter than its star, not trillions. Still brutal, but possible. Its MIRI instrument operates at 7 Kelvin, near absolute zero. And it carries a coronagraph, a star blocker with millionths of a degree precision. In August 2024, they pointed Webb at Alpha Centauri A, blocked the glare, subtracted B's light, applied algorithms to separate real signals from artifacts. They found something, a blob 10,000 times fainter than the star, orbiting at 2 astronomical units, twice the Earth-Sun distance, at the edge of the habitable zone. The numbers suggested a gas giant, mass comparable to Saturn, ammonia and methane clouds, not a place to walk or where life could arise directly, but a planet, the closest ever directly photographed around a sun-like star. And then something strange happened. In February 2025, they looked again. The planet had vanished. April, nothing. As if it never existed, scientists ran simulations of millions of possible orbits. They asked, under what circumstances would it be visible in August, but invisible afterward? Answer. In half the stable orbits, the planet would have moved too close to the star to be detected. It didn't disappear. It hid in the stellar glare. In 2019, another telescope had caught a fleeting glimpse of something there. At the time, it seemed anomalous. Now the pieces fit together. If the planet exists, still unconfirmed, it orbits in an elliptical trajectory through the habitable zone. Feynman would have found this deliciously ironic. For decades, models said planets there were impossible. And now we had evidence of one doing exactly what it shouldn't. The universe showing it knows things our models haven't learned yet. But here's what really unsettled the scientists. It wasn't the planet's existence. It was what that existence implied. A gas giant orbiting through the habitable zone is a gravitational disruptor. Imagine a cosmic bully marching through the playground, pushing everything it encounters. Rocky planets trying to maintain stable orbits would have to deal with this giant passing periodically, pulling them, distorting trajectories, potentially throwing them out of the system. Alpha Centauri. A probably doesn't have an Earth hiding there. The giant wouldn't allow it. But that doesn't mean there aren't interesting places. Saturn has over 140 moons. Jupiter, nearly 100. Some, like Europa, Enceladus, Titan, are considered the most promising places for life in the solar system. Not because they're in the sun's habitable zone, but because they have their own energy sources. Subsurface oceans heated by tidal forces. If the candidate planet is real, it could have its own moons, dozens, and some could have conditions we haven't imagined. Feynman loved this kind of twist. You search for one thing and find something completely different. The answer isn't what you expected, but it's still an answer. And there was Proxima Centauri to consider. The red dwarf already had confirmed planets since 2016. Proxima b, an Earth-sized world in the habitable zone. The discovery sent waves of excitement through the scientific community. The nearest star system had a potentially habitable planet. But complications emerged. Proxima is a flare star, violent eruptions that increase its brightness tenfold in minutes. Torrents of radiation washing over any nearby planet like cosmic tsunamis. Proxima b receives 30 times more ultraviolet radiation than Earth, 250 times more X-rays. Over billions of years, this radiation could strip away any atmosphere. Or maybe not, if the planet has a strong magnetic field like Earth, deflecting the worst. We don't know yet. Feynman would have appreciated the uncertainty. He always said not knowing is more honest than pretending certainty. Science lives in the space between questions and answers, not in the answers themselves. What we know is this. In 2019, the ALMA radio telescope detected a massive flare from Proxima, 10 times brighter than the largest solar flares. If Proxima b was on the wrong side at that moment, it was sterilized. And these flares aren't rare. They happen several times a month. Life is resilient, though. On Earth, we found organisms in boiling hot springs, Antarctic ice, lightless ocean abysses. If life arose on Proxima b, it could have found underground refuge, could have adapted in unimaginable ways. The problem is, we can't go there to check. Not in our lifetimes, probably not in our great-grandchildren's lifetimes, or can we? There's a project called Breakthrough Starshot. The idea is to send tiny probes, weighing only grams, propelled by light sails. Powerful ground-based lasers would push these sails to 20% of light speed. At that speed, Alpha Centauri would be a 20-year journey. A probe launched when a child is born would arrive before they finish college. The challenges are immense. Building gram-scale spacecraft that survive 2 decades in interstellar space. Creating laser arrays powerful enough, navigating with absurd precision across trillions of kilometers. But engineers are working on it, testing prototypes, refining designs. Feynman said nature's imagination is far greater than man's imagination, but he also said man's imagination is the only tool we have to reach it. The candidate planet around Alpha Centauri A, if confirmed, would be the first concrete target. Not just a star, but a world, a real destination. Psychology matters. Having a specific goal motivates in ways vague aspirations never can. And even if we never physically arrive, each observation teaches us something about ourselves. About how planets form, about where life can arise, about our place in the cosmos. Feynman used to say the first principle is not to fool yourself, and you're the easiest person to fool. He applied this to physics, but he also applied it to something larger, to how we look at the universe and at ourselves. For most of history, we believed we were the center of everything. Earth was fixed. The sun revolved around us. The heavens were perfect and unchanging. We were creation's purpose. One by one, these beliefs were overturned. Copernicus showed Earth moves. Galileo revealed imperfections on the moon. Darwin demonstrated we evolved from other life forms. Hubble proved our galaxy is one among billions. Each discovery was disorienting. Each made us smaller. But each also freed us from comfortable illusions to reveal genuine wonders. The discovery of planets around Alpha Centauri, if confirmed, will be another such transformation. We'll no longer be inhabitants of the only known planetary system in the neighborhood. We'll have neighbors. Worlds 4 light-years away that existed throughout human history without our knowing. Stars that shone over pyramid builders, over Greek philosophers, over every human who ever lived and looked skyward with wonder. Alpha Centauri was there all along, keeping secrets. And now, for the first time, we're beginning to read them. Feynman died before seeing the first confirmed exoplanets, before Hubble, long before James Webb. He worked with his era's tools and imagined future tools. We are that future. The golden mirrors floating silently beyond the moon are extensions of calculations he and others made decades ago. The fundamental physics, allowing detection of a light point 10,000 times fainter than a star, is built on foundations Feynman helped establish. There's something recursive in this. The universe produces matter. Matter organizes into stars. Stars forge heavy elements. Elements combine into planets. Planets, at least one, develop life. Life evolves consciousness. Consciousness builds telescopes to look back at the stars that created it. You're made of atoms forged in stellar furnaces billions of years ago. The carbon in your bones, the iron in your blood, the oxygen in your lungs, all of it was once part of stars that exploded before the sun was born. And now, those atoms are looking at Alpha Centauri, trying to understand their distant cousins. What Feynman saw, what truly unsettled him, wasn't the impossibility of getting there. It was the terrible beauty of that unreachable proximity. A gift the universe offers with no intention of delivering. A promise that might never be fulfilled. Or maybe it will be. The coming years will bring more observations. The candidate planet will reappear in its orbit, or it won't. It will be confirmed or discarded. New telescopes will search for smaller, rocky, potentially habitable worlds. Science advances one step at a time. Sometimes it stumbles, sometimes it retreats, but it always moves, and we move with it. Feynman once wrote that we're not afraid to look at the unknown, that it's possible to live without knowing all the answers, that we don't need to pretend certainty where doubt exists. Alpha Centauri is doubt crystallized in starlight, a question traveling 4 light years to reach our eyes. The universe saying, here's something, find out what it is. And we're finding out, slowly, patiently, with golden mirrors and mathematics, and that peculiar stubbornness that defines the human species. The stars will keep shining long after we're all dust. But while we're here, we'll look at them. We'll ask what they are. We'll dream of reaching them. Feynman understood this better than most. The joy isn't in the answers. It's in the search. Alpha Centauri waits, as it always has. And we, finally, are learning to see what it hides.